We're so excited and happy to have him here with us. Let's give a huge round of applause for Gavin Wood.
Thank you. Cheers. Nice to see so many of you are able to turn up. How was it so far? This is the third day, right? We've had modularity and education or something. How is it so far? Good? Yeah? Good. Right, I didn't really know at what level everyone is at. Like this is, so it's a bit of a mixed bag of a talk. I'm going to cover basically everything from the bottom to, why we're doing it, all the way up to the top of like exactly what it is that we are doing right now. I think I've got quite a long time, so I guess it should be okay. How many, just to get a feel, how many are non-developers here? How many people here have not written any code? All right, so maybe a third or a quarter. Okay, I'll do my best to make it digestible. And how many are already familiar with Jam and like maybe they have flicked through the grey paper or whatever? Okay, like maybe half. Cool. Alrighty. So starting at the bottom, like why are we bothering to do this at all? It's part of this concept originally laid out 10.5 years ago. Called post-Snowden Web or Web3, and since sort of developed into a more broad set of maxims, sort of a broad coda, top of which is resilience, right? And it's resilience that means that like the Bitcoin network is still going, it hasn't been like, I don't know, broken or shut down or whatever. Unstoppability might be another word for resilience if you want, but I quite like resilience because it folds in, it's a bit more neutral, and it doesn't necessarily assume someone wants to stop it. And I think it's important also to understand which of these maxims are Web3 specific. Like resilience is probably the most Web3 specific of the maxims. I would argue that actually there are a couple of other maxims that are relatively specific to Web3. But I mean, that's a little bit more debatable than the resilience one. So the next two are like generality and performance. Generality is like what of the jobs you might want to do on it, of the uses you might want to make of it. How many of them is it applicable for? And Bitcoin obviously was not the most general of solutions. It was pretty limited in its scripting functionality, and Ethereum really opened that up. That was a big contribution to Web3 in terms of this second maxim, whilst retaining the resilience part, right? And then we kind of got a little bit the performance, and particularly performance and coherency, kind of got a little bit stuck. I'm going to talk a little bit more about the performance and coherency because this is really where Jam comes into the equation. And accessibility, which is sort of a lot of things muddled together. Accessibility in terms of developer accessibility. What do the APIs look like? What are the guarantees that you get from the system? But also in terms of like human user accessibility. Are there any? How easy is it for people to actually use the system? Do they have to like go into a centralized website first to buy a token? Do they have to understand some other, I don't know, set of concepts first, some vocabulary before they're going to be able to use it? Are there like national or jurisdictional boundaries on usage? Right, there's a lot of questions for accessibility, and many of them are, I believe, addressable technologically. Perhaps not all. Okay, and accessibility, I think, is, together with coherency, are both partially deficient in Web 2. Again, there's an argument to be made, well, actually, there's Systems in Web 2 can be made coherent even if they're run on disparate servers. And similarly, Web 2, it's very accessible. So 4 billion people on Facebook or whatever. It's kind of like, yeah, but then it's actually in Web 2 very easy to shut services down and say, well, for this jurisdictional boundary, it's actually inaccessible for this population. So I think, again, arguments on both sides there. But Web 3 really, the maxims of Web 3 are to try to provide all 5 of these in as much as possible. So JAM, how does JAM fit into the Web 3 concept? Well, JAM is a trustless supercomputer. That's what JAM is, right? The clue is in the M. It's a machine. Yeah. The J and the A specify how the machine works, but it is a machine. It's a virtual machine. It's a machine that runs computer code. And generally we call these things computers. It's a supercomputer because it's got lots and lots of cores, lots of performance, lots of storage facilities. And it's trustless because you don't need to actually trust anyone to use it. And this trustless supercomputing facility forms a basis for, if you like, a Web3 cloud. What is a cloud? Well, basically it's somewhere where you can run services. And therefore, because it's trustless, there are no servers. I kind of mean servers in a kind of more anthropocentric fashion. So there's people serving your thing. There are no servers in this sense. There are no companies of people that you're paying to run your service, like AWS or Google Cloud or whatever. And as a trustless supercomputer, it combines 2 key functionalities that we see in computers, which is data, data storage, data hosting. In our case, there's 1.6 petabytes projected of data that it can host, with an ability to fetch about 2/3 of a gigabyte per second from that data store. And compute functionality, which is a bit harder to measure, but roughly, let's say, between 1/4 and half the speed of 341 AMD Threadripper CPUs, roughly. And if you want to put that into Ethereum terms, roughly, and EVM is very hard to pin, EVM gas is very hard to pin down, but if you want something back of the envelope, then about 1 trillion gas per second. So let's look at how it fits into the wider world. Ethereum L1. I mean, it's 10 years old now. It's not going to compare very well, but it's in here for anyway. It's costly. It costs a lot to use, and it's very low performance for what it is. I mean, it was very good at the time, but as with most computers that were very good at the time, 10 years later, they don't really stack up that well to the competition. And we can compare. We can then say, well, actually, let's they got this roadmap of having lots of separate blockchains, L2 blockchains, as they say, that would be hosted or secured at least by Ethereum L1, the original, the main Ethereum network. But the L2s are all kind of separate organizations, separate individuals, separate companies, maybe even that are running these networks. Which leads to a very patchy feeling if you want to actually use more than one L2. It's because they kind of do work in different ways, they kind of have different guarantees, potentially also kind of different different APIs, different sets of additional functionality that they might give, which can be seen as an advantage. It's the market taking over and kind of doing different things all at the same time. But can also be seen as a disadvantage if you want to build a coherent solution. More importantly, the L2 model, or many L2 model, results in persistent partitioning of state. If you consider this as a single system, then each L2 actually is a subsystem that is persistently separated from the other L2s in terms of what data it can access, right? And this is kind of part of the mantra of sharding. Yeah? This is like something that also, I'll come to it in a second, but it's something that Polkadot has really pushed forward with. Polkadot did it many years before Ethereum, but like this concept of like taking a large system, splitting it up into shards, separate bits, and then keeping them sort of separated persistently is results in what I'm calling a high level of incoherence. Also, one of the sort of things that Ethereum is sort of vaguely making its way in the direction of is trying to scale its computation and data availability facilities with zero-knowledge cryptography, which, in a few years may possibly become viable, but at the moment is, and probably even in a few years, is going to be heavily centralizing, and at the moment is also extremely costly. Okay, so Polkadot, how does this stack up? And when I say Polkadot, I mean Polkadot up until like now, not Polkadot, going forward necessarily. Well, Polkadot, particularly within its parachains model, also had this persistent state partition, right? Polkadot as a parachains host, or if you like, as a blockchain hosting solution, had this persistent state partitioning because the parachains each have their own state, right? They're run as separate endeavors, and moving things between them is hard, right? Now, Polkadot 1, as we are calling it now, also had pretty high barriers to entry because you generally have these 2-year leases on slots and a relatively restricted number of slots. That's less of an issue with Polkadot, what we're calling 2, with its agile core time, which massively reduces the barriers to actually utilizing Polkadot as a blockchain hosting system, but the persistent state partitioning remains a sort of a disadvantage. Some alternative approaches, one of which is bridging chains, right? So basically having totally independent chains and then just having bridges between them. Generally like client bridges, relying on the proper operation of each other's validator set in order to gain any kind of security. Generally, this is an insecure way of doing things. You are essentially you're putting quite a low price on what we might call causal poisoning. Basically, making an event happen in one insecure chain in order to have a knock-on effect in a otherwise very secure chain. Yeah, and this, if you want to build this as a whole system, as a coherent system, then you're going to end up with causal poisoning, which means your system is insecure. You can attack the system by choosing a weak point, and you've still got this persistent state partitioning, right? Ultimately, the data that one chain has directly accessible to it is almost totally inaccessible to another chain, notwithstanding very particular and generally costly oracleization mechanisms. We can also just say, well, let's soup up the servers, right? Let's soup up the validators and try and make them really close together, give them super fast interconnects, and turn the validator network into something that looks much more like a sort of centralized, hosted sort of service. And you're going to end up with still something that is synchronous. So that's kind of very helpful for developers. And you will, if you soup up the validators and you ensure their interconnects are good, and you don't care too much about like keeping your old data available, and you don't care too much about bringing on new validators who would then need to synchronize everything, then you can get quite far. But ultimately, you will hit the glass wall, the glass ceiling of what you can what hardware you can expect validators to have, what level of connectivity to other validators you can expect them to have. Generally, it's going to be less resilient because it's less decentralized. There's less diversity within your network, and it's going to be it's going to naturally be centralizing as it's harder to gain entry into this clique since synchronizing becomes very difficult. Since you probably need some very good connectivity to the other agents that are validating. So how does Jam compare? Well, Jam is a multi-core multi-core compute model with a shared state that is mostly coherent, right? So it's not quite fully synchronous, but it's also not persistently sharded. It's a mostly coherent shared RAM, shared storage. This allows Jam is designed to be highly decentralized still. Because it's multi-core, it can really host, can do a lot of computation within its compute model, which is necessarily going to be a little bit more complicated than your average synchronous compute model, just because asynchronous programming is more complicated. But because it's decentralized, we get that, we still have this, high degree of resilience. And the real key word here is mostly coherent, right? That's what we are finessing in order to get this high level of performance while still having resilience. So if we go back to the Web3 maxims, with Jam, we're not focusing too hard on, we resilience, yes. Generality, yes. And accessibility, yes. We think, these are more or less we have good solutions for them. They're kind of solved within the Web3 sphere, or at least the solution exists, and Jam is trying to utilize that. These two, performance and coherency, are a lot harder to address together. Because it turns out there is a bit of a universal conundrum, universal sort of phenomenon, which is an antagonism between the size of a system and how coherent it can be. They're pulling in different directions. As systems grow, they become incoherent, just necessarily. There's not much we can do about it. You see it all over the place. In biology, a single cell could not grow to the size of a human, right? It wouldn't work anymore. Nutrient densities would be so massively different across the cell. The way that the nutrients get in would be so, it just wouldn't work, right? It's like, just try and imagine it, it doesn't work. Works at its own particular scale. But if you want to have something bigger, then we have to just take that and kind of multiply it out and have a multicellular organism. Yeah, can't just grow the cell indefinitely. And similar animals don't take their sort of base biology when they're very small and just scale it indefinitely. An example of there would be the move from cold-bloodedness to warm-bloodedness. Yeah, again, in order to allow for a degree of coherency despite the size. Yeah, basically optimizing that coherency, trying to make it as great as possible despite the size of the system. You can see it in physics as well. Right? The speed of light essentially gives us the trade-off between coherency and size. As things get farther apart, they get more distant in terms of their causality. It takes longer for them to cause any effect on each other. Yeah? Like when we talk about in the quantum space, it's essentially instant. Yeah? We can have instant effects. The speed of light doesn't come into it. But as soon as we get beyond that into the classical world and beyond, then we have to respect the speed of light, which is essentially, as I say, the coherency that we get or the incoherency that we get as our systems grow. And we can see this again with like the speed of electricity, and this actually becomes, when our systems are running very, very fast and are very, very complicated, running across like a large amount of silicon, then actually this becomes an issue. And we need to start optimizing how the size of our paths and the difference in distance of our paths on our silicon. Yeah? Because otherwise we lose coherency even in this tiny little space. We see it also in like CPU design, like beyond that, like computer design. The memory that one particular CPU core sees may be different for any given single point in time to what another CPU core sees, right? This represents a lack of coherency. As the system grows and we have more CPU cores, they actually may have different views on memory, and then we need to manage that reduction in coherency somehow. So how do we manage incoherency? Well, the most obvious way is just to divide things up, right? So instead of having a shared memory, we have one CPU with its memory and another CPU with its memory, and then if they want to do anything together, they kind of have to send a message over the network or something. That will be one way of doing it. Similarly, instead of having, an amoeba twice the size, we have just two amoebas. Bacterium twice the size, just have two bacteria. In a database, we may just have different databases, or we might be a little bit clever and have a single database but with different shards. Yeah. But it's usually this way of like dividing in some persistent fashion our system into separate subsystems. But if we do this, and especially if we do it naively, it reduces our ability to compose, it reduces the alignment of the overall system and the ability for the system to coordinate within itself. It can do so to a degree that makes certain, that removes certain abilities from that system. But there are more nuanced ways of managing incoherency. We might have, for a multicellular organism, shared DNA and some very complex signaling system using, hormones and nerve cells and all the rest of it, right? That's one way of managing the incoherency that this division into subsystems implies. Big organisms might develop blood vessels, right? Warm-bloodedness in order to spread nutrients very effectively and manage the environmental conditions so that they're more or less the same across the organism. For CPUs, we might have separate memories for each core, like the caches, right? But then we might have some very clever sync primitives and data logistics so that when they need to see a coherent state of the memory, they can. Yeah? And that's, in fact, how modern CPUs work, modern multi-core CPUs. So they kind of get this impression of coherency, even though there may be some price to pay in terms of asynchroneity, right? In terms of latency, in terms of stalling. And this is essentially what Jam does. It tries to take this nuanced approach to incoherency and make it mostly coherent. We're not going to be able to make it fully coherent, at least not yet, and probably never, because if you look at all the other examples of big systems, none of them are fully coherent, none of them are fully synchronous. It just doesn't exist in the real world. When you want the system to grow, you have to absorb some incoherency. The question is, can you do it well enough to keep all of your old use cases working? So how does Jam nuance this incoherency? Well, basically it copies some concepts from modern multi-core, multi-CPU machine design. So it has a sort of shared memory storage, if you like. But at any given time, each core, which is in Jam, which is more or less analogous to a CPU core, may see slightly or may have slightly different perspective on that storage. That perspective will ultimately resolve, and for any given particular point in storage, once resolved, it can continue with whatever workload that wants to use that storage. In this sense, very similar to a CPU. And then there is a concept of a fully coherent element, which is essentially like a sort of database that is synchronous, right? That is atomic and synchronous. And if you want to compare it to like a regular machine, then it's essentially a 341 core CPU with aggregate memory bandwidth of about 682 megabytes a second and aggregate RAM of about 1.6 petabytes, right? That's more or less, if you want to get a feel for what kind of a machine it is, there you go. And then it's got a database sort of subsystem. It's fully coherent, fully synchronous, atomic, and this allows at about 2.5 megabytes a second and 1 million ops a second, right? With about a one-core CPU level of scripting capacity, scripting capability. So, crucially, cores have access to common storage. Yeah? There is like a common, I don't want to say state, because that sort of implies that it's synchronous, that at any given point, the state is absolutely fixed, knowable, universal. It's not quite. But there is a concept of a common storage, and that will ultimately resolve into something that is knowable. A little bit like, so it's a little bit of a superposition if you want to actually measure it at any particular time, but you know that after not very long, it's going to resolve. That storage is addressable in 4K pages, which is very handy if you want to run virtual machines using this storage. And these 4K pages are actually addressable in two different ways. A long-term address format, which is a cryptographic commitment, and a short-term addressing mechanism, which is an export reference, which is basically a reference to the thing that put the workload that put the data in the storage. If you don't necessarily know what the data is, you just know that this workload made it, then you can reference it for a period just by that workload reference. Crucially, there is an affinity for certain elements of storage with certain CPUs. This is a little bit like having data in like an L1 or an L2 cache for a CPU core, right? It makes it faster, it reduces the possibility of that core stalling when it wants to access this. So if you want to do like lots and lots of work on a particular, piece of data or series of intermediate results, as long as it's on the same core, it's not going to stall. If you move it to a different core, then there's going to need to be some like background work to basically get that data ferried across so that some other core can continue with it, right? And this is, again, very similar to what happens on a CPU. A process will typically execute on a single core because that core's cache will already be loaded with all the stuff that the process needs to go. Jam services are the discrete, if you like, persistent workload that exists on the Jam computer. Essentially, you can think of them as a process, right? It's like a process on the Jam computer. Yeah. It's got some similarity with smart contracts. It's kind of more of a passing similarity than anything that you should read too deeply in. Jam provides what I call a persistent object model environment, which is basically, if you know about like object-oriented programming or whatever, then it's sort of that environment. If you know JavaScript and the sort of JavaScript environment like this, right? You can create objects. Those objects have code and data, yeah, and generally only they can access their data. This kind of thing. And it's trustless, like a smart contract platform. But there are very important differences that mean that you can't really sort of take everything that you know about smart contracts and just translate it into Jam. Firstly, it's a multi-core execution model, which means smart contracts or services, not smart contracts, services may be operating simultaneously, right? There may be code executing simultaneously. Yeah? So that's the first thing. Second, it's asynchronous. It's not, when execution happens, it doesn't necessarily result in a synchronous alteration to the state of the machine. Execution of different services may happen, may intentionally happen sort of synchronously or co-scheduled. That's what it's called here, because they're basically scheduled at the same time in the same core. Co-scheduling a service or two different services enables for a possibility of synchronous composition within its main workload. This is very useful. And this kind of runs against that asynchronous point. This is, in fact, the only way that you can really synchronously compose until you fall back on band-aids, like having sequencers do the synchronous composition. And portions of work, packages of work, are orderable. So you can say, well, I need this thing to be done before that thing. In terms of like purchasing computation, the purchasing of gas, it's done with a fixed size workload or a bundle workload. So you can have many different discrete smaller workloads for different services, but when you bundle them all together and basically shove them into the machine for execution, that is a fixed size of workload. So there's a fixed amount of gas and a fixed amount of data I/O. And you purchase this in bulk. Purchasing is very similar to what Polkadot has at the moment, agile core time. It's just instead of giving a sort of slice to a parachain, you instead give it to a quality of workload. Now, I'll come to that in a second. It's essentially you restrict what workloads can be done on that core at that particular point in time. A Jam core looks a little bit like this, if you want to visualize it. Most importantly, I/O. I/O, any point in that past month, a Jam core can fetch up to 2 megabytes a second of that data and basically push out 2 megabytes a second of data back into this storage system, which can be accessed at any time in the future month. As I said, there is core affinity, which means accessing this data is generally going to be immediate if it's on the same core and might take a block or two if it's on a different core. The core itself runs around 25 to 50% of native speed, and this will depend on optimizations that will happen probably ongoing over the next 2, 3, 4 years. But current expectations are about this speed. If you want like EVM gas, it's hard because like different operations on the EVM translate to different effective times that it takes, like an average x86 processor to execute. But roughly, each core has between like 500 million and 5 billion EVM gas a second, right? And that's each core. We have 341 of them. And each core has about 8 kilobytes a second of output bandwidth into the database. Now, the database then has its own scripting processor, right? Its own scripting core that can then do stuff with this 8 kilobytes a second of data. This scripting core can do about 1 million accesses into the kind of coherent synchronous database a second. There's also this separate pre-image lookup system, which essentially gives you free data lookups for the price of holding it on chain. So there's a deposit price that you have to pay for this. So if we look into the Jam service pipeline, so what do Jam services do and see? It's basically 4 pieces of computation that need to be done. The first 2, the first one is authorization. Let's jump into this. First one is authorization. This just makes sure that the workload that is going to be done is actually paid for, right? That's all. Very simple. It's a very small piece of code. When you buy core time, like as you buy core time on Polkadot now and you sort of attach it to a parachain or trade it and then eventually attach it to a parachain, in Jam you're not attaching it to a parachain because Jam doesn't know what parachains are. Instead you attach it to a kind of workload. And you can write the code for recognizing kinds of workload, right? That's a Turing complete thing that you can do. So you just write whatever, Rust code, whatever, anything that compiles to PVM, and you can decide in the code whether a workload is valid or not. And it's this code that runs in the authorization stage. Next stage is what we call refine. Refine is basically the main stage, right? It's like the part of the pipeline that you do all of your work, all the computation. You decide, you use the CPU, you use the core, you read from the big storage, you write into the big storage, and you eventually decide what needs to be written out also to the synchronous atomic database, right? Then you move into the accumulate stage. The accumulate stage is basically the database stage. But the accumulate code is basically the script for taking the output of refine and doing something with it, with the rest of Jam, right? With the synchronous composition facilities of Jam. It's not really synchronous, but it's more synchronous than in refine. Finally, there's the transfers, which accumulate code can kick off. And this is essentially a handler script for any cross-service signaling that, again, need to be done in a fully coherent fashion. So it's synchronous. It's not really synchronous, but it is fully coherent. Yeah? Everything that's done in accumulate and transfers is done on-chain and therefore has an absolute valid state of the world. Now, there's a bit of a difference between accumulation and what I'm terming integration. And this is a point that will be developed on further, but I'm touching on it now for those of you who are actually sort of using Jam or coding up Jam seriously, and you want to know what maybe cross-service interoperation looks like. So cross-service interoperation is essentially where you have 2 different services that want to do some interaction. This is going to be very important for the composition of services, right? 2 different services could be like totally different services, like a parachain in a parachain service and a smart contract in a smart contract service, and they want to interoperate. Or it could be 2 different conceptual elements, each within the same service, potentially. It's more relevant for different services, but potentially could be useful for the same service as well. Now, accumulation is a concept provided by Jam. It's this, as I say, it's a piece of computation, an I/O that happens within a totally coherent environment. So where you can, in some sense, interact with the rest of Jam coherently. It's not synchronous, which means other things might be happening at the same time. So there's a limitation to what you can do. You can essentially only change your own services database state, right? Your own services storage. But it's nonetheless, you do get access to looking at other services in Jam. Their current storage, not really current because they might be doing something in the meantime, but it's like the last snapshot of their storage. And initiating transfers. Transfers are essentially small messages that may come with a token, a balance transfer as well. Integration is something that is service dependent. For example, a parachain service, integration might mean that the parachain's, a particular block of a parachain is now the finalized head of that parachain. Yeah? Now, accumulation and integration are different things. Accumulation can integrate immediately the apparent repercussions, but they might also queue the repercussions for integration later, perhaps dependent on some other service doing some of its own integration. Yeah? Or also dependent on some other things within the service. Yeah? For example, a parachain, continue with the parachain example, it might be that the block of the parachain that is going to be finalized is actually on a fork. And actually, you can't finalize it yet because you want to see which one is going to be longer. Or it might not have a parent done on the chain yet, and you want to kind of keep it around in case the parent turns up. In any case, there may be multiple different outcomes for any given accumulation that will only resolve at some point later. And because of this, you don't want to, if two services have been co-scheduled and kind of have will have different accumulation, each have their own accumulation, I should say. You don't want one to get integrated when the other might not get integrated. Yeah? If it's two parachains exchanging tokens, you want either both of them to get integrated and the token exchange to go through, or neither of them. But if one accumulates and the other only might accumulate later, or rather, if in the accumulation of one it integrates, and in the accumulation of the other it may only possibly integrate later, then you have an issue. And this is why we may possibly need some support within the Jam protocol for managing atomic integrations, basically. Managing the atomic outcomes of accumulation beyond accumulation itself. It may also just be part of the SDK. It may just be a sort of set of conventions that we use. That's up in the air, and we'll probably need to really prototype some services on Jam to understand better if this is needed as a primitive as part of the protocol, or can just be done on the protocol in an SDK or whatever. All right, got like a little bit of time left, so I'm going to discuss where we are at the moment and where we're going. So Jam, grey paper, spec of Jam. It's been through 4 minor is not quite the right one, 4 big version changes. 0.1 was the initial draft that was released back in April in Dubai. 0.2 introduced what we call segmented DA, which is basically everything I've said. All of this stuff to do with 4K pages and month-long periods in the shared storage. This is all based. Segmented DA is what created all of this. 0.3 introduced a few final elements into the protocol that were needed: statistics, disputes, privileges. 0.4, which was released not that long ago, introduced ordered accumulation, which meant essentially was created the possibility of having cores of Jam have affinity with certain elements of storage, right? Without this affinity, without this kind of L2 or L1 cache of Jam cores, we will stall when we try to fetch our previous exports into our previous writes into our storage back again in the following package of work, right? It's a little bit like before ordered accumulation, we were always writing everything to RAM, waiting until this was coherent across all of the CPUs, and then if we wanted to read what we wrote back, and then getting it back. If we wanted to read something else that wasn't being used, that wasn't recently written, we wouldn't stall. But if we were doing some long workload that was always writing some intermediate thing out and then reading it back in again, then we would stall a lot. And for this, we needed some affinity, right? Basically, we needed a cache. And in reality, that's what ordered accumulation provided to the protocol, the ability to have this affinity, and therefore, essentially by having this kind of cache. 0.5 is in the works. It's almost finished, and it introduces a few important elements that have been on the issue list for a little while. Largely tweaks that have been informed by implementing the protocol thus far. Right? And it's like, oh, when you implement it, you're like, oh, actually, it turns out it would be really handy if this thing happened after that thing, not before. Or this piece of data was actually in here. It saves us a lot of work. And that's basically what we did. The additional focus on 0.5 was alterations to the Polka VM, right, this PVM. The main change was moving from a 32-bit register architecture to a 64-bit register architecture. This resulted in a number of new instructions and 1 or 2 removals. And there's also introduced into the grey paper is the concept of memory pages of the PVM. Everything is split into 4K pages, and these pages, their accessibility, which is either read, write, or inaccessible, is based on the page, like whole pages, not bytes, right? Not individual bytes, which is what it was before. There's a couple of new host calls, and a couple of new operations distinct from the register change. Memset and memcopy optimizations, basically. Right, 1.0, path to 1.0, what does it look like? 0.6, I'm planning on basically it just being tidying up of the grey paper. There's certain formalization things I want to change. 0.7 will be tweaks probably coming from real-world tests on the Jam toaster. 0.8 probably will be coming from real-world services written. And then 0.9 is, total freeze other than security fixes. Okay. So diving a little deeper into that. So the 0.6 focus is basically on having a comprehensive and complete spec, which includes putting the networking protocol into the specification, possibly altering the Merkle, at the moment we use Merkle mountain ranges, possibly altering the format of Merkle mountain ranges for optimizing basically light client and cross-chain implementations of the Jam protocol. Improvements in the formalization, which basically means doing the references properly for things like grandpa and some of the cryptography, deduplicating a few bits. And really trying to get to a point where the test vectors for at least milestone 1 are complete. It's not really a grey paper thing, but it sort of ties in. 0.7 release focus will be on what we discover after trying out the Jam protocol on the Jam toaster. I very much expect there to be networking optimizations, additional network messages, alterations to pre-existing message formats in order to get it running as fast as possible. There'll probably be a erasure code optimization for one of the 2 usages that we have of erasure coding. Probably will be optimizations over how we move data around the network. In particular, for those of you who are Jam literate, we will probably be doing some structured gossip of work reports and not distributing the work reports in the final block. We'll sort of pre-distribute them. And there will quite possibly be tweaks to the PVM. Post 0.8 is really when the period that we will be developing these initial services on Jam and like testing them out, seeing how well they work, how easy it is to develop them, how well they can interoperate, if any changes need to be made for that. This is potentially where that accumulation integration difference we might decide actually we need some protocol functionality for integration. There may also be tweaks to the PVM to facilitate certain services. Most likely the parachains service. Maybe tweaks to the distributed availability system. I don't know. There's a lot of question marks here because we haven't actually prototyped any services yet. 0.9 focus will be on security and any discoveries we get from actually real-world usage in the Canary network. Talk a little bit about service development on Jam. Very soon we'll be releasing the first first SDK for developing Jam services. Very, very simple, right? It's like, I don't know, a couple files of code. It's not a lot of code, but it will allow people to start seeing how services are built, like how they're structured in code. And then over the coming, 12, 15 months, we will see the different, the first few services that at least Parity is aiming to build, and not to say others cannot build. Of course, everyone can build services, but like these are the ones that we have sort of slated. This year, should get our initial bootstrapping service published. So on testnets, we're able to stick in the Genesis block this service, and this allows us to basically create new services and deploy new services onto the network. Like Jam doesn't have any concept of like deploying a service, right? There's only what's in the Genesis block and what services actually do. But the Jam protocol itself doesn't have any facility for this. Also doing things like designating validator group, assigning core time, creating a new super user service, introducing a services that are privileged, so-called always accumulate services that always run, transferring balances, and interacting with the pre-image system. That's core boot. That's a very simple service. This one is almost already written. Next one I'm calling Core VM. This is a really fun test service. This is going to be the first real demonstration of Jam's capabilities. Basically, Core VM is designed to be a service that runs a PVM binary, any PVM binary. All right? So any binary, any executable that you can target to PVM, which basically means any executable you can target to RISC-V, right? Which basically means any Rust language program or any C++ or any C language program that you want to write or whatever. Anything that can use LLVM, basically. You can deploy into Core VM. I mean, it has to be like no STD. Don't expect that you're going to have like keyboard input or anything. Yeah, any PVM program that doesn't assume all of the fancy operating system services should be able to run on-chain. Crucially, this means it can have indefinite execution, i.e. it's not limited in terms of gas or I/O, right? It doesn't have any special storage facility. It just has memory, yeah? It just has like regular 32-bit addressable memory. That memory is cunningly split up and stored in the DA in Jam's 1.6 petabytes of storage, and paged in as it's needed. And it's also scheduled just as it's to execute, and then suspended and resumed as you would expect it to be if it ran on a regular operating system. And I think it's with Core VM that we can start demonstrating that Jam is actually a lot more similar to a real silicon machine than any blockchain has come so far. Yeah? And the eventual way of attempting to demonstrate that this is a real machine is, of course, trying to run Doom on it. This is what we're going to try and do. We're going to try and actually run Doom, and I don't know if we're going to actually pump out the frames, but the Doom itself, we want to run in core on Jam, like on chain. Yeah. Following Core VM is the next up prioritization-wise is Core Chains. This is essentially a mostly compatible version of the relay chain. Say mostly compatible. Can't make it perfectly compatible, just because there are differences in data formats and things. But the idea is that it's sufficiently compatible that Cumulus can be upgraded to provide a compatible API to existing parachains that will then be able to use Jam for their essentially hosting, their security hosting, right? So replacement for the relay chain functionality. I mean, when we say there's, I think next year we're going to see a lot of changes in terminology around Polkadot. We already see some of this being discussed on the Polkadot on the forum, and largely I think it makes a lot of sense. In particular, parachains. Really, what we're going to see, I think, my preferred terminology once we start thinking of Polkadot post Jam is that we don't have like parachains per se. We have blockchains, L1 blockchains, yeah. And then what Jam provides is a hosting service for L1 blockchains that gives them security, message relaying, and finality, right? That's like kind of makes sense. So it just kind of demystifying a lot of what Jam does. And this means that we can start thinking of Jam as like something that you write services on, and one of which is, you know, securing blockchains, but there can be other services, yeah? Because Jam is, at the end of the day, not a blockchain of blockchains, but a multi-core supercomputer, right? And there's a few things that this can result in, but essentially this concept of accords, which is smart contracts like entanglement of blockchains, is something that Jam should be able to provide. Following that, core play. This is by far the most ambitious of the things that we want to write on Jam, and it will follow from the core VM and basically allow the different VM instances to send messages to each other and be dependent on each other and even do synchronous composition with each other. Yeah, and this, therefore, it's like kind of an actor framework, right? An actor platform, and those actors, in principle, can be like different paradigms. They can be like PVM actors. They can be EVM-style smart contract actors. They can be indefinite executing programs like Doom, right? They can be basically whatever you want because it's just a general virtual machine. And then, yeah, in principle, you'd be able to choose between synchronous composition, which basically means co-scheduling, or async composition, which means they don't need to be co-scheduled. They do something much more similar to like maybe XCM, or they may even do some suspend resume thing where they actually we have good asynchronous programming primitives, as you might expect in sort of regular languages, futures and promises and all that sort of thing. Good. Final little bit. I know I'm slightly over, but 2 more slides. Grey Paper Prize is going much like I'm actually quite surprised. There's now 32 registered, declared implementation teams. There they are. It's quite a lot. It's like substantially more than I was expecting. I was kind of thinking maybe 10 would be a good thing to aim for, but like, all right, nice. And of these, actually, we are seeing teams getting into the M1 area. So basically doing all of the ability to sync a blockchain. M2 is where you can actually be a validator node. And we're seeing a few teams maybe getting halfway or so, even to M2. So this is very encouraging. Well done, you 32 teams. I will be continuing the Grey Paper tour next year. Basically, once I'm happy that the Grey Paper is at more or less a final state, we'll announce those dates, but expect there to be a fairly substantial number of venues in Asia. I've so far only covered the on-chain elements of the Grey Paper, so the first, I don't know how many sections, 14 or something. The next series of the tour will be more focused on the off-chain and appendix parts of the grey paper, although I will cover the on-chain things, but I'll mostly just cover the parts that I've changed since the last set of lectures. And that's it. I hope you enjoyed the lecture, the presentation. Cheers.
Thank you. Thank you very much, Gavin. Hey, Gav, before you go, do you have time to take a few questions?
Yeah, sure.
Okay, let's do it. If you have a question, throw your hand up. Try to make it a question that will help us all understand what was just presented better. Anybody have a question for Gav?
Afterwards.
A question right there? All right, here you go.
Sorry for this. What to press? Okay. So thanks for your presentation. I have a quick question. So I'm a big fan of Tron and Telegram ecosystem. And my question is, what is your stance, how we can, cooperate between Tron and Polkadot? What is your opinion there?
I'm not super familiar with Ton beyond the original white paper, like, I don't know, 6-7 years ago. But in general, Jam's written with the ability to have light clients run on other networks for secure bridging. This is really a sort of key element in the design of Grandpa, right? And Beefy, which is our sort of optimization stage of Grandpa that consolidates signatures into something very manageable. So I would hope that at least on that side, there's ample potential for building bridges.
Okay, thanks.
Anybody else? Yep.
Talking about light clients, for Small.dot, the light client for Polkadot, like how much needs to be changed in that code base to like make it work for Jam?
It's difficult to say. I'm not overly familiar with the code base, but in terms of protocol changes, which is probably informative, I would say less than 50% of the necessary of the necessary code that would need to be written for Small.dot is different for Small Jam, right?
And will then also like, would it then be able to verify like any, I don't know, like finalized state for any other service user?
Precisely, yeah. So in the model of Jam, as I present that circle thing with the inner circle, basically light client stuff. So Small Jam only looks at what the fully coherent part of state is, which is that middle bit, right? It doesn't look at this 1.6 petabyte storage facility, like memory of the machine. It looks at just this kind of this atomic database, this coherent database, sits in the middle. And yeah, anything that is in there is what Small Jam would be able to query. In principle, if it knows what to look for in the bigger storage, the 1.6 petabytes, it could also do that probably on a separate kind of DA querying layer. But the important thing is to really get the ability to have this up-to-date coherent view of the center database.
So that it knows it's true, that it exists.
Yeah.
All right, how about one more?
Hey Gavin, it's great to watch you talk here. Actually, watch your talk at DevCon 1. And one of the things that I've been like echoing for a long time is like you said a global singleton, which I think is probably one of the coolest things that it's sort of like gone out of the terminology in recent years. But I'm recently with my friends working on Rise Chain. We're doing a lot of optimizations on the CPU, and we had to talk about asynchronousness. And I'm really curious as to how, like, if you could drill down into how you've actually been able to achieve, like, the asynchronousness. And then my second question is, do you think you've finally achieved that truly global singleton computer with what you're building here?
I mean, it is what it is. It's a trustless supercomputer. Is it going to scale infinitely as it stands? Probably not. I mean, because there's still an element which is coherent. There's the middle bit, right? And that only scales so far. Like that still has the same limitations that any coherent system will have, any fully coherent system will have. So in order to scale beyond there, we probably want something a bit more. I mean, you can probably just increase the number of validators and size of validator nodes and stuff. Eventually, as I mentioned in the talk, you're going to hit a glass ceiling. So scaling always has to be scaling out, and then the question is how can we introduce the concept of affinity so that the bits of a system that don't need to be very close to each other, for a period of time at least, don't have affinity and are separate and are incoherent, but the bits that do need to interoperate with each other are, for a period of time at least, are coherent. And doing this in an agile fashion is really the trick. And this is what like Jam is introducing afresh. Yeah, there's like we actually have a strategy for working, like dealing with the incoherency that comes about as we scale. Polkadot's strategy for that was just split everything out. Polkadot 1 strategy is split everything out into discrete systems that can only interoperate at a fairly high latency, low bandwidth, highly asynchronous way, XCMP. And this is problematic for a lot of use cases and just generally developing. And it also, because you have persistent state partitioning, you force teams to select which bit of state they want to be in forever. No one wants to make that decision, right? No one wants to make a forever decision, certainly not coders. Yeah? And so what we need is an agile way of rearranging the affinities that are enjoyed by the different parts of our overall state, not just sticking them, like bundling them into one box that they can never leave from. And this is this general problem is a problem faced by everyone that is not just trying to soup up validator nodes. Yeah, everyone that wants to legitimately scale out. Yeah, and as I said, from what I've seen in other ecosystems, particularly Ethereum, there's still not really a recognition of how to deal with the incoherency from this, parallelized scaling, from this scaling out.
That's super cool, man. I love what you guys are doing here. It's awesome.
Cheers.
Thank you very much for the question, and thank you very much, Gav, for coming on and sharing this with us today.
Thank you for your attention. Cheers. And thank you, Sub0 Reset team.